Alrighty, lots of questions today, so let's get through to them. Go ahead and pull up the list of the questions. So let's start with 74A. So in 74A, we have this farmer setting up a fence, and the farmer is setting up a fence that has this rather weird shape. So we have this rectangle, which is h high, and this half circle with a radius of r. So this side is 2r. And so we want to know, with 200 feet of fencing, sorry, 600 meters. I don't even know where the 200 came from. 600 meters of fencing. What choice of R will maximize the area? Okay, and the question here was specifically about setting this up, figuring out what is the thing I'm optimizing and what is the constraint. Okay. So the thing to optimize, and in this case maximize, is area. And so I have to write down what is the area. And so in this case, I actually gave you a pretty fleshed out picture so that we can figure out the area in this case is going to be the area of the rectangle, which is 2RH, plus the area of the semicircle at the top, which is going to be pi r squared over 2. So it's pi r squared over 2 because it's half of a circle, not a whole circle. So that's the thing I'm trying to optimize. Meanwhile, my constraint here is that I'm using 600 meters of fencing. So I'll go ahead and write fencing equals. And so if I go ahead and add up the fencing, that's 2r fence, plus those two together are 2h fence, plus, and then this is half the circumference of a circle of radius r. So remember, the circumference of a circle is 2 pi r. So that is to say this is half of that, so that is plus pi r. And this constraint is that this is 600. So we have to solve the constraint for our choice of R and H. And it's probably a little easier in this case to solve it for H. So if I do that, I'll go ahead and say, okay, so 2H equals 600 minus 2r minus pi r. And I can go ahead and plug this in for 2h up here in this formula. If I want, I could solve for h by dividing both sides by 2, but notice I'm immediately going to multiply it by 2 because this is a 2h that's actually in my formula. So I'm just not going to bother dividing, and I'm going to try and keep that in mind. We'll see if I can remember for the 10 seconds it takes me to write out the word substitute. So I'm going to get area is R times 2H plus pi r squared over 2. So I can simplify that a bit. So that'll be 600 r minus 2r squared minus pi r squared plus pi r squared over 2. So minus pi r squared plus pi r squared over 2, that's just going to be a net minus pi r squared over 2. Because these two are both multiples of pi r squared. And so once I've written this down as simply as I reasonably can, I take the derivative. And so that in this case will be 600 minus 4r minus pi r. And then I set this equal to 0, and I solve this for r. So I can go ahead and move all the r stuff over to the right. So that will give me 4r plus pi r equals 600. I can factor out the r. So that will give me r times 4 plus pi equals 600. And so finally, I should get that r is 600 over 4 plus pi. And in this particular problem, that's all it actually asks you for. So that is our answer, because it asks what choice of r. We've given them the choice of r. (75A). 75A is a look up your formulas from geometry that you might not have thought about before, or not have thought about in a bit, questions. So 75A says you're making an oil can, and so we want to make a cylindrical can it is going to hold 1,000 centimeters cubed of oil. And we want to know what is the least material that we can use to make this. All right. So in this case, our thing to optimize is, in this case, we're minimizing the amount of material. If you think about the amount of material in a can, this is really talking about the surface area. And so the surface area of a cylinder is this. If you don't know these formulas, by the way, it is a good idea to put these formulas on your note sheet just in case they come up on the test. And so then my constraint is that the volume has to be 1,000 centimeters cubed. And so the volume of a cylinder is pi r squared h, and that has to be 1,000. So there's our thing to optimize. There's our constraint. We want to solve our constraint for one of the variables. So that will give us h is 1,000 divided by pi r squared. I would definitely solve for h and not for r. for the reason that it makes the algebra here simpler. If I wanted to solve for r instead, I would need to take a square root. So there is my solving the constraint for one of the variables. I'll then substitute that into the surface area, which will give me that the surface area will be 2 pi r times 1,000 over pi r squared plus 2 pi r squared. This will simplify a bit. The pi's will cancel, one of the r's will cancel, and so this will work out to be 2,000 divided by r plus 2 pi r squared. Once I'm here, I have to go ahead and take the derivative of this. And so the derivative here will be minus 2,000 over r squared plus 4 pi r. And again, we want to know when that's 0. So we'll get 2,000 over r squared equals 4 pi r. So that will give me 4 pi r cubed equals 2,000, which will give me, if I divide both sides by 4 pi, that r cubed is 500 divided by pi. And so r will be the cube root of 500 over pi. And I will leave it there for you to answer the rest of the question. Okay, 76a. So 76a is one of these questions where we've got a graph here. In this case, it is y equals 16 minus 2x. And we've chosen a point here on this graph. I'll go ahead and call that point x comma y. And we've drawn this rectangle here. And the question is, what point here maximizes the area, and then what's the area? So my thing to optimize here is area. Which in this instance is x times y. And my constraint is that the point has to be on the line. So my constraint here is that y equals 16 minus 2x. So this is already solved for y, so I can substitute that in. And so I will get area equals x times 16 minus 2x equals 16x minus 2x squared. So the derivative here will work out to be 16 minus 4x. I want to know when that is 0, which gives me 4x equals 16, which gives me x is 4. When x is 4, I look back to my original equation or my constraint, whichever one you want. They're the same thing. And I plug in 4, and so I learn that y is 8. And so that means the point in question is 4, 8, and the area is 32. And last up on the list of questions that people submitted, we have 77A. So I think I'll have done almost one of each, actually. Maybe literally one of each, actually. 77A. So here, this asks, what point on the graph of y equals 2x plus 1 is closest to the point 4, 4? And so to do that, I want to note that I'm looking here at, again, this line and some point that is below it. And so I'm looking at some point on this line and looking at the distance between those 2 points. So here in this case, I am minimizing the distance, for which I need the distance formula. So d equals the square root of x minus 4 squared plus y minus 4 squared. And we're doing that subject to the constraint, again, that the point I'm looking at is on the line, so that is that y is 2x plus 1. Okay, so I have to plug 2x plus 1 here into this formula. So that will give me d is equal to the square root of x minus 4 squared. I'm just going to go ahead and FOIL out while I am doing this. So that is x squared minus 8x plus 16 plus 2x plus 1 minus 4 squared, because I put in that value for y. This is the same thing as x squared minus 8x plus 16 plus 2x minus 3 squared. Let's continue foiling. So that's plus 4x squared minus 12x plus 9. And so if I combine all of this, this works out to be 5x squared minus 20x plus 25. That's my d. So d prime here is going to require the chain rule. So if I do the chain rule, I'm going to end up with the following. So the derivative of square root is 1 over twice the square root of the thing. And then I need to multiply by the inside derivative. So in that case, this is 10x minus 20. And so if you go ahead and now solve for when this is 0, we look at the numerator. And we'll get that x is 2. And when x is 2, if I look back at the fact that y was 2x plus 1, I get that y is 5. And that is it for this question. Let's see. I see a couple other questions that have snuck in, so let's talk about those. Let's look at, so while we're at it, let's look at 77B. So this same question, but part B, where the algebra is maybe slightly more complicated. And then I also have a request for 75B, which we can go back and peek at after this. So for 77B, we want the closest point to 4, 1 on the graph of y equals x squared over 2. So in this case, I want to minimize this distance. Which by the distance formula is this. My constraint is, again, that the point is on the graph. So in this case, the constraint is y equals x squared over 2. And so I can go ahead and substitute that back in. So that is going to give me the square root of x squared minus 8x plus 16 plus, and then this will be x squared over 2 minus 1 squared. Okay, so we'll do a bit of algebra. So this will be x to the 4th over 4 minus x squared plus 1. And so that is going to give me that the distance is equal to, so the x squareds cancel. So I will have square root of x to the 4th over 4 minus 8x plus 17. So I need to use the chain rule to take the derivative of this, but when I do, I'm going to get this. Maybe more like that. And the derivative of the inside here is x cubed minus 8. So I end up here solving x cubed minus 8 equals 0, because again, I'm only looking at the numerator. And x cubed minus 8 equals 0. That happens only when x is 2. And so when x is 2, it turns out y is also 2. And so that gives you that the closest point on the graph is 2, 2. I also see a 75B. Let's see, which is 75B. So 75B is the cylindrical can question that we did before, but backwards. So now we have 100 centimeters squared of material. And we want to know what's the largest volume that we can make. And so, in this case, we're optimizing volume. In this case, we're maximizing it, which is still pi r squared h. And the constraint now is the surface area, which is 2 pi r h. plus 2 pi r squared equals 100. So I need to solve this for my choice of variables. I think the variable that's going to be easier to solve for is going to be h, so I'm going to do that over here. So I will get 2 pi r h equals 100 minus 2 pi r squared. And so h is going to be 100 over 2 pi r minus 2 pi r squared over 2 pi r. And that's going to say that h is 50 over pi r minus, and then that's just going to simplify to r because the 2's will cancel, the pi's will cancel, and the r will cancel with one of the r's. So that's my solving part, and I can plug that back in to my volume now. And so that will be pi times r squared times 50 over pi r minus r. And if I do that, I'll get pi r squared times 50 over pi r. That will work out to be this. And then minus what will just be pi r cubed. So the volume here, just to spell that out more cleanly, is 50r minus pi r cubed. And so I need to take the derivative of this and set it equal to 0. Which will be that. I'll set that equal to 0, and I will get 3 pi r squared equals 50. So r is the square root of 50 divided by 3 pi. Okay, and I'll leave you to do the rest of it from there. All right, I'm here for the next hour and a half, aside from I have a short meeting with an advisee that I could only squeeze in, so I will duck out briefly during this. But otherwise, if you have a question, just drop it in the chat, and I will answer it as soon as I can.